Hi, I'm Elham. I'm a researcher at Eindhoven University of Technology in the process mining domain. We have prepared some tutorial videos to introduce the tools and techniques that have been developed in this domain for those who are interested to apply these techniques in their business or do further research about them. In this specific video, we are focusing on one of the process discovery techniques called Heuristics miner. Heuristics miner takes an event log as input and discovers a process model that describes the control flow perspective of a process that was captured in the event log, showing the relationship between the activities. The heuristics miner allows for finding complex relationship between activities that other basic algorithms like alpha miner are unable to discover. The models that are discovered by heuristics miner gives a general overview about the process in question, and the miner can even handle big event logs. The introduction tutorial that can be found in the video link below already describes the basic use of the plugin without explaining the technicalities of the algorithm. In this video, the inner workings of the plugin will be discussed, and the parameters that can affect the resulting model will be analyzed in detail. Before we discuss the algorithm behind the miner, let's first see what are the basic relationships between the activities that can be observed in a process model. Suppose we have two activities, A and B. The activities can be in a direct sequence relation, A directly followed by B. Or they can be in an indirect sequence relation with other activities occurring in between, A indirectly followed by B. The previous constructs can also happen in a loop. A follows itself, or A followed by B is repeated. A and B can also happen in more complex relations, in parallel, or in a choice relation. In a parallel relation, both activities A and B can happen in any order or even at the same time. Choices can have two flavors, either exclusive or inclusive. In an inclusive choice relation, either of the activities could happen alone, but it is also possible that both activities happen. In an exclusive choice, only one of the activities occur. The heuristics miner can identify all of the previously discussed relations between events. The heuristics miner has a specific detection method for detecting these constructs. It combines these constructs and creates a process model. For these constructs, there is no specific detection mechanism. However, they can be identified by looking at the frequency with which activities occur. This figure shows the main steps that the heuristic miner goes through while discovering a model. In the rest of this video, we will explain the details of each of these steps. We will first explain how to detect all the direct sequence relations. Suppose we have an event log with 16 different types of traces. The number of occurrences of each trace and which activities they contain are shown on the left. In the matrix on the right, all the activities that occur in a log are displayed on the X and Y axis. The cells show how often an activity from the Y axis is followed by an activity from the X axis. For instance, this cell shows the activity C was directly followed by activity D 57 times in the whole log. Using the following formula, we compute the heuristic values for every direct sequence dependency relations. The formula takes into account the number of times an activity A is followed by an activity B, minus the opposite, everything divided by the sum of both values plus 1. Filling in the formula will give a real value in the range of -1 and 1, indicating the strength of the causal dependency between activities A and B. Notice that the value for the direct sequence relation between B and A is exactly the negative of the value of the relation between A and B. The heuristics miner allows for setting 3 parameters to control the direct sequence dependency relation between activities. These are the dependency threshold, the relative to best threshold, and all task connected heuristic. The dependency threshold sets a limit, so we only can keep the relations having a heuristic value above the limit, which will then show up in the model. This parameter is configurable by the user. In our example, if we set it to 90% and the rest of the parameters as shown in the screenshot, every relation having a heuristic value below 0.9 will be discarded. As you can see, the values above the threshold have been colored in green and represent the relations we accept. For every green value, we create an edge between both activities. Therefore, we obtain this model. As is seen in the model, the connection between B and C is missing because the value of this connection is 0.62, which is lower than the threshold. Let's try with a different set of parameters to see how it influences the discovered model. If we set the dependency threshold to 60%, the dependency value between B and C is above the threshold, so it will lead to an edge in the model, as can be observed. Now we are going to explain how the parameter all task connected functions. So we return the dependency measure to 90%, removing the connection between B and C. Basically, when we check the all task connected parameter, the algorithm assumes that it is not allowed to have activities to have 0 input or output edges, apart from the initial and final ones. Hence, it uses the dependency relation with the highest value to create at least one input and output edge for every activity, even if it's below dependency threshold. For instance, consider all the values observed in the second row, which represents all the heuristics for the relations identified following the occurrence of activity B. The highest observed relation is B to C with a value of 0.62. According to the dependency threshold, this value is not accepted. Now, if we choose all tasks connected, it will be accepted and will lead to an edge from B to C in the discovered model. The next configurable parameter is the relative to best threshold. The best relation with the highest value for each activity row is selected. Then this parameter determines which is the admissible distance between relations and the best one in the order to be accepted or discarded. Keep in mind that this parameter is applied to the result of previous steps in which values are filtered out according to the dependency threshold. In this case, with the relative to best parameter set to 0%, every value except the best ones for every row will be discarded. So in this example, we miss the relation C to E and F to H, as can be observed in the resulting model. On the other hand, with the relative to best threshold set to 2%, 0.97 will be accepted in addition to the best 0.98, because the distance to 0.98 is in the range of 2%. We will now discuss the input parameters for the detection of the loop relations. First, we will talk about the procedure to detect loops of length 1. To do so, the metric is different from the one used for the direct sequence relations. This time, we count the number of times that an activity is followed by itself. Then this value is divided by itself plus 1. Therefore, only the diagonal of the matrix is filled. Setting the parameters as the ones shown in the screenshot with a value of 90% for the length 1 loop threshold, we see that 0.96 is above it, which corresponds to the loop for activity A. The effect can be seen in the resulting net. Now let's see how to detect loops of length 2. This matrix is different again. This time, we count how many times the sequences ABA and BAB are observed. The value is divided by itself plus 1. If we set the parameters as the ones in the screenshot with a value of 90% for length 2 loops, we obtain a length 2 loop between activities B and C. For this threshold to have any effect, the checkbox Ignore Loop Dependency must be unchecked. We will now discuss the input parameters for the detection of the long-distance relations. The long-distance dependency is calculated in relation to a new metric, called the eventually followed by relation. It measures the amount of time that an activity A is followed at some point in the trace by an activity B. We see in the matrix on the right side that A is eventually followed by B 129 times in the log, which matches the amount of time that A happens in the log, as can be seen in the vector in the left side. This means that every time that A happens in a trace, it's always followed by B at some later point in time. Now let's set the parameters to the ones shown in the screenshot with a value of 90% for long-distance relations and checking the long-distance dependency heuristic box. We see that 5 relations are above the threshold. However, only 2 are relevant and added to the model. The reason to discard the rest is that the model does not allow the first activity to happen without executing the second one at some point in time before the end. So it can be seen in the model that every time that A is executed, B and C will eventually happen. The same happens for F and I. If D is executed, there is the option to skip G by executing first F and then H instead of G. Therefore, a connection between E and H and between D and G will be added to the model. Now you're ready to use Heuristics Miner. If you're interested in more videos about process mining, please check out our website, processmining.org. Thank you very much for watching this video, and I hope to see you in the next video.